46 billion light-years away, something impossible is happening. Light that left the edge of space when time began is arriving right now at your eyes. Beyond that border, galaxies are tearing away faster than physics should allow, frozen forever at a boundary we will never cross. But the real edge is closer than anyone thought. We are sitting inside a bubble 2 billion light-years wide, where reality itself is thinner, where thousands of galaxies should exist but do not. If you're enjoying this journey to the borders of everything, hit that like button and subscribe. Prepare yourselves. We begin. 46 billion light-years away, in every direction, lies a boundary called the observable horizon. Beyond it, nothing can be seen, not because our telescopes are weak, but because light from those regions has not had enough time to reach us since the universe began 13.8 billion years ago. This creates a sphere around Earth, a bubble of visibility. Everything inside can theoretically be detected. Everything outside remains forever invisible, no matter how long we wait or how powerful our instruments become. You might think the edge should be 13.8 billion light-years away, matching the age of the universe. But space itself has been expanding while that ancient light traveled toward us. The sources of the oldest light we detect today have moved much farther away during the journey. Picture a photon leaving a distant galaxy when the universe was young and small. As it races toward us at light speed, space stretches beneath it like a cosmic treadmill. The galaxy it left recedes deeper into the void while the photon fights forward. By the time that photon arrives, the galaxy sits 46 billion light-years away, nearly 3 times farther than the simple calculation would suggest. This boundary is not a wall or a membrane. No physical barrier marks the spot. It is simply the geometric consequence of having a universe with a finite age and a maximum speed for information. Light carries information, and information cannot travel faster than light. Therefore, a maximum distance exists from which information could have reached us. The observable horizon shifts constantly. Every second, light from slightly more distant regions enters our sphere of visibility. Our cosmic view expands, but not without limits. Some parts of the universe are moving away from us so rapidly, accelerated by dark energy, that their light will never arrive. Those regions lie beyond a different boundary entirely, one that contracts rather than grows. But we will reach that edge soon enough. For now, understand this. The universe you can see is not the universe that exists. The observable horizon is like standing on an ocean shore, seeing only to where the sky meets water. Beyond your sight, the ocean continues. Similarly, space extends past our horizon, filled with galaxies and structures we cannot detect. We occupy the center of our own observable universe, but every point in space is the center of its own sphere of visibility. What lies beyond our horizon? More galaxies, more clusters, more cosmic web, possibly forever, possibly not. We cannot know, and that is precisely what makes it an edge. The particle horizon is the ultimate boundary of the observable universe. It marks the distance to the farthest matter whose light could have possibly reached us since the Big Bang. Right now, that distance is 46.5 billion light-years. This is not the same as the age of the universe multiplied by the speed of light. Cosmic expansion complicates everything. When the universe was very young, space inflated faster than light for a brief but violent period. During those first fractions of a second, regions of space that were initially close together were torn apart at superluminal speeds. This inflationary epoch stretched tiny quantum fluctuations into cosmic scale structures. It also meant that light emitted from certain regions took a very long journey to reach us, even though the universe itself was small at the time. Think of the particle horizon as a growing sphere centered on Earth. When the universe was 1 second old, this horizon was tiny. Only light from extremely nearby regions could have reached us. As time passed, the horizon expanded. Light from more distant sources had time to arrive. Today, 13.8 billion years later, We can see light from objects that were once much closer, but have since been carried away by expansion to 46 billion light-years distance. The cosmic microwave background radiation represents the edge of the particle horizon in a practical sense. This radiation comes from a time 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. Before that moment, space was opaque, filled with plasma that scattered photons. We cannot see past the cosmic microwave background because there was nothing transparent to see through. It forms a glowing shell around us, the oldest light in existence. But even the cosmic microwave background is not the true edge. The particle horizon extends slightly farther in principle, though we lack the means to observe it directly. Neutrinos and gravitational waves from even earlier moments could theoretically reach us from beyond the microwave background, carrying information from closer to the Big Bang itself. Those signals would define the absolute edge of our particle horizon. One strange consequence: the particle horizon is always growing. Every moment, light from slightly more distant regions crosses the threshold and becomes observable. Our cosmic view expands outward, like ripples on a pond. However, this growth has a limit. In the far future, as dark energy dominates and accelerates expansion, fewer new regions will enter our view. Eventually, the particle horizon will stop growing and begin to shrink. Galaxies will disappear beyond our reach. The particle horizon defines what we can observe now, but there is another boundary that determines what we will ever be able to observe, no matter how long we wait. That boundary is closing in. While the particle horizon shows what we can see today, the cosmic event horizon reveals what we can ever hope to see in the entire future of the universe. That boundary is much closer, only 16 billion light-years away. Beyond it, galaxies are lost forever. Here is the cruel mathematics. The universe is not just expanding, but accelerating its expansion, driven by dark energy. Galaxies farther away recede faster. At a certain distance, they recede so quickly that even light leaving them today, aimed directly at us, will never arrive. The expansion of space carries that light backward faster than it can travel forward. Those galaxies lie beyond the cosmic event horizon. Imagine a swimmer trying to reach shore while the current pulls them backward. If the current is weak, the swimmer makes slow progress. If the current equals the swimmer's speed, they stay in place, swimming furiously but going nowhere. If the current exceeds their speed, they are swept backward despite their best efforts. Light from galaxies beyond the event horizon faces that losing battle. Today, the cosmic event horizon sits at 16 billion light-years. This seems paradoxical. Our observable universe extends to 46 billion light-years, yet the event horizon is closer? How can we see things beyond the event horizon? The answer is time. We can see those distant galaxies because we are detecting light they emitted long ago, when they were closer to us and still within the event horizon. We are watching their past. But if you could observe one of those galaxies beyond the current event horizon, you would see something strange unfold. As you watch over billions of years, the galaxy would appear to slow down. Its stars would age more and more slowly from your perspective. Its light would redshift, becoming dimmer and redder. Eventually, the galaxy would seem to freeze in time, its image fading to darkness. The last photons it could ever send us would arrive, and then silence. The galaxy would vanish from the universe as far as we are concerned. This creates a deeply unsettling future. As cosmic acceleration continues, the event horizon will stabilize at approximately 17.6 billion light-years, and then begin to slowly contract. Galaxies currently visible will cross that boundary one by one. In hundreds of billions of years, nearly every galaxy beyond our local group will have disappeared beyond the event horizon. Future astronomers will look up and see almost nothing, a dark, empty cosmos with just a few nearby galaxies. The cosmic event horizon is a one-way door. Once a galaxy crosses it, no signal from that galaxy can ever reach us again. We are causally disconnected, severed by the relentless expansion of space. The universe divides into islands that can never communicate. Something impossible is happening right now. Astronomers can observe galaxies moving away from Earth faster than the speed of light. This seems to violate the fundamental rule of physics. Nothing can exceed light speed, yet we see it constantly in distant galaxies. The resolution of this paradox lies in understanding what is actually moving. Special relativity, the theory that sets the cosmic speed limit, only applies to objects moving through space. It says nothing about space itself moving. Space can expand at any rate. In fact, space expands everywhere, all the time. The farther away you look, the more space lies between you and a distant object, and therefore the faster that object recedes from you as all that intervening space stretches. Consider two galaxies separated by 1 billion light years. The space between them expands, adding perhaps 50,000 miles every second. That sounds like a lot, but spread over 1 billion light years, it is a tiny percentage increase. Now consider two galaxies separated by 10 billion light years. 10 times more space lies between them, so 10 times more expansion occurs. The recession velocity grows proportionally with distance. Beyond a certain distance, recession velocity exceeds light speed. For our current universe, that threshold sits at about 14 billion light years, a distance called the Hubble sphere. Galaxies beyond the Hubble sphere recede faster than light, yet we can see many of them. In fact, most galaxies in our observable universe have always been receding faster than light, even when they emitted the light we now detect. How is this possible? Because the light did not have to outrun the recession velocity. The photons were carried along by the expansion of space, like messages in bottles floating downstream. Although the galaxy recedes faster than light, the space between us and the galaxy is expanding, and that expansion eventually brought the photons closer to us. As they traveled, they entered regions of space where recession velocity was slower, until finally they reached our local neighborhood, where recession is minimal. This creates a bizarre situation. You can observe a galaxy that is receding at twice the speed of light. You are detecting light from when it was receding at only 1.5 times light speed emitted when it was closer. That light has been traveling for billions of years, during which the galaxy accelerated even farther away. If you sent a signal back to that galaxy today, your signal would never arrive. The galaxy has crossed the cosmic event horizon. The cosmological horizon paradox forces us to rethink motion itself. Recession velocity is not motion through space. It is motion of space. The galaxies are not flying through the universe at superluminal speeds. They are carried by the universe's expansion. Nothing local moves faster than light, but on cosmic scales, the rules change. Space itself becomes the ocean, and we are all adrift on its currents. Understanding this paradox is essential. The edges of the universe are defined not by distance alone, but by recession velocity. Some edges mark where things move away too fast for light to ever reach us. Other edges mark where light from the past still arrives, but light sent now never will. Picture a galaxy sitting just beyond the cosmic event horizon today. Light leaving that galaxy in our direction will never reach us. But something stranger happens to the galaxy itself. From our perspective, it appears to freeze at the boundary of visibility, suspended forever at a single moment in time. This is not metaphor. As a galaxy approaches and crosses the event horizon, the light from its later moments is redshifted more and more severely. Redshift stretches the wavelength of light, which also stretches the time between photons arriving. Imagine watching a clock in that galaxy. The clock ticks normally in the galaxy's own frame of reference, but from Earth, each tick takes longer and longer to arrive. The clock appears to slow down. As the galaxy reaches the event horizon, the redshift approaches infinity. The time between photons becomes infinitely long. The last photons from that galaxy will take forever to arrive. We see the galaxy frozen at a particular moment, its image growing dimmer and redder as those final photons struggle across the expanding void. Eventually, the galaxy fades completely from view, but technically, It never finishes crossing the horizon from our perspective. It asymptotically approaches the boundary. This creates a gallery of frozen images. Every galaxy beyond a certain distance is visible only as it was billions of years ago, locked in the past. We see young galaxies forming their first stars, ancient galaxies caught mid-collision, structures that have long since evolved into something unrecognizable. The farther we look, the younger the universe appears. The cosmic event horizon is a window into history, but also a trap. Those galaxies cannot escape their frozen state. Meanwhile, from the perspective of someone in that distant galaxy, Earth is the one receding beyond their event horizon. They would see us slow down, freeze, and fade. Neither perspective is more correct. Each observer is trapped behind their own cosmic horizon, unable to influence or even detect what lies beyond. The expansion trap grows tighter over time. As dark energy continues to accelerate cosmic expansion, more galaxies cross the event horizon. The observable universe does not shrink immediately because we still receive light that left those galaxies long ago. But the list of galaxies we can still theoretically communicate with grows shorter. In the distant future, nearly all galaxies will have crossed our event horizon. Imagine astronomers 1 trillion years from now. They look up and see only a handful of nearby galaxies. Everything else has vanished, redshifted into darkness. Those future observers might conclude they live in a small, isolated universe surrounded by infinite empty space. They would be wrong. Countless galaxies exist beyond their horizon, thriving and evolving, but forever unreachable. The expansion trap would have sealed them into a cosmic prison. This is not science fiction. This is the measured fate of our universe. Unless dark energy changes its properties, which is possible but unconfirmed, the cosmic event horizon will continue contracting. Galaxies will continue disappearing. The universe will empty itself before our eyes. Earth does not sit in a typical region of space. We are inside a bubble, a vast underdensity of matter called the KBC void, or local hole, stretches around us for nearly 2 billion light-years. This supervoid contains 20% less matter than the cosmic average. Thousands of galaxies that should exist simply do not. Cosmic voids are common. They form naturally as gravity pulls matter into dense filaments and clusters, leaving empty spaces behind. The universe resembles foam, with galaxies concentrated in sheets and strands while voids fill the gaps. But the KBC supervoid is unusually large. It ranks among the biggest known structures in the observable universe, and we are sitting near its center. This creates a problem. The standard model of cosmology predicts that matter should be distributed relatively evenly on large scales. Small variations exist, but they have limits. A void as enormous as the KBC supervoid pushes the boundaries of what should be possible under standard physics. Some cosmologists argue it is an unlikely but acceptable fluctuation. Others suggest it reveals cracks in our understanding. The supervoid affects everything around it. Galaxies on the edges of the void are pulled outward by the dense matter beyond the boundary. This creates peculiar velocities, motions that are not caused by cosmic expansion, but by local gravitational attraction. For us inside the void, this means nearby galaxies appear to recede slightly faster than they would in a uniform universe. The void adds an extra push to their apparent motion. This has profound implications for measuring cosmic expansion. When astronomers observe supernovae in distant galaxies to calculate the Hubble constant, they assume those galaxies are moving purely due to expansion. But if we sit in a supervoid, local galaxies are also being pulled away by the denser matter beyond. This could make the local expansion rate appear faster than the cosmic average. It might explain the Hubble tension, a discrepancy between different methods of measuring how fast the universe expands. Some researchers go further. They suggest the KBC supervoid is so large that it cannot form under standard gravity. Perhaps gravity works differently than we think. Modified theories of gravity, like modified Newtonian dynamics, can produce larger structures more easily. If the supervoid is real, and confirmed to be as large as measurements suggest. It could be the first direct evidence that our theory of gravity needs revision. But there is debate. Not all astronomers agree the KBC supervoid exists or is as large as claimed. Measuring cosmic density is difficult. Galaxies are easier to count than dark matter, and dark matter dominates the total mass. The void might be less extreme than it appears if dark matter fills it more than expected, or it might be even larger. Surveys continue, mapping more galaxies to refine the void's size and depth. One thing is certain, we do not live in an average place. The universe is not uniform. It has structure, texture, variation, and Earth happens to occupy a particularly empty neighborhood. 700 million light-years away lies the Boötes void, a spherical region 330 million light-years across, nearly empty of galaxies. Astronomers call it the Great Nothing. Inside this void, where 2,000 galaxies should exist, only 60 have been found. The rest simply are not there. The Boötes void was discovered by accident in 1981 when astronomer Robert Kirshner and his team were mapping galaxy redshifts to create a three-dimensional picture of the universe. They expected to find galaxies scattered throughout space. Instead, they found a massive blank spot. At first, they thought it was a mistake, an error in their data, but deeper observations confirmed it. The void was real. Voids form naturally in the cosmic web. After the Big Bang, tiny quantum fluctuations in density created regions slightly denser and regions slightly less dense. Gravity amplified these differences. Dense regions attracted more matter, growing into galaxy clusters. Less dense regions lost matter to the surrounding areas, becoming voids. Over billions of years, small voids merged into larger ones, like soap bubbles combining. But the Boötes void is extraordinarily empty even for a void. Most cosmic voids contain at least 15% of the average matter density. The Great Nothing appears to have significantly less. The few galaxies inside are not randomly distributed. They cluster in a tube-like structure running through the center of the void, suggesting the void may have formed from several smaller voids merging together. Standing inside the Boötes void would be a lonely experience. If Earth were located there, the night sky would contain almost nothing. A few faint smudges marking distant galaxies along the edges, but no nearby neighbors. No Andromeda galaxy dominating the view. No Magellanic clouds. Just darkness. Astronomers on such a world might have developed very different ideas about the universe, concluding they lived in a small island of galaxies surrounded by infinite emptiness. The void itself is not completely empty. It contains gas, dark matter, and a handful of galaxies. But the density is so low that structure formation is suppressed. Gravity needs matter to work with. In the densest regions of the universe, matter collapses into galaxies quickly. In voids, there is too little material. The few galaxies that do form are small and dim, struggling to grow. Why does this matter? Because voids are sensitive to dark energy. Dark energy accelerates the expansion of the universe, and its effects are most noticeable in low-density regions, where matter's gravitational pull is weak. By studying how voids evolve and expand over time, astronomers can learn about dark energy's properties. The Boötes void, being so large and empty, is an excellent laboratory for these measurements. The Great Nothing is not unique. Other large voids exist, but it remains one of the most dramatic examples of how uneven the universe truly is. Galaxies are not sprinkled uniformly through space. They cling together in filaments and clusters, leaving vast deserts between. In the cosmic microwave background, the oldest light in the universe, there is a scar. A region of sky in the constellation Eridanus, about 10 degrees across, is colder than it should be, 70 millionths of a degree colder than the average. This might sound insignificant, but on cosmic scales, it is a massive anomaly. Astronomers call it the CMB cold spot, and nobody knows what caused it. The cosmic microwave background radiation comes from 380,000 years after the Big Bang. At that moment, the universe cooled enough for electrons and protons to combine into neutral atoms. Light that had been trapped in plasma suddenly streamed freely through space. That light, stretched by cosmic expansion into microwaves, reaches us today from all directions. It shows us what the universe looked like when it was young. The CMB is remarkably uniform. Temperature variations are tiny, only about 1 part in 100,000. These tiny fluctuations are the seeds of galaxies, regions slightly denser or less dense that grew into the structures we see today. But the cold spot is different. It is larger and colder than statistical models predict. Its existence is improbable. One hypothesis suggests the cold spot is caused by a supervoid between us and the CMB. When CMB photons travel through a void, they lose energy due to the integrated Sachs-Wolf effect. They enter the void, climbing out of the gravitational potential, which robs them of energy and cools them. Normally, they regain that energy, falling back in as they leave. But if the void is expanding rapidly, driven by dark energy, the photons exit into a shallower potential well than they entered. The energy is not fully recovered. The photons remain colder. Astronomers searched for such a void and found candidates. The Eridanus supervoid, if it exists, would be enormous. 500 million to 1 billion light-years across, 6 to 10 billion light-years away, a region with significantly less matter than average. But measurements are controversial. Some surveys detect the void clearly, others find only weak evidence. The debate continues. Other explanations have been proposed. Perhaps the cold spot is a cosmic texture, a defect left over from a phase transition in the early universe, like a crack in ice as it freezes. Perhaps it is evidence of quantum entanglement with another universe, a speculative idea that most physicists consider unlikely. Perhaps it is simply a statistical fluke, an outlier that happens to exist in our patch of sky but is not physically meaningful. The cold spot remains unexplained. It is a piece of the puzzle that does not fit, and when a piece does not fit, it usually means something interesting is happening. Either our models are incomplete, or something unusual occurred in the early universe, or we are missing a fundamental piece of physics. The CMB is supposed to be smooth and predictable. The cold spot suggests it is not. And if one anomaly exists, there could be others. If the Eridanus supervoid is real, it is one of the largest structures in the universe, a region stretching 500 million to perhaps 1 billion light-years across, lying between 6 and 10 billion light-years away. A vast underdensity of matter that would help explain the cold spot in the cosmic microwave background. But its existence is disputed. Detecting cosmic voids at such distances is extraordinarily difficult. We cannot see dark matter directly, and dark matter dominates the total mass. We infer the presence of voids by counting galaxies. If a region has fewer galaxies than expected, we assume it is a void. But galaxy surveys are incomplete. Distant galaxies are faint. Small galaxies are missed. The data is noisy. Some surveys show a clear dip in galaxy counts toward the direction of the cold spot. Fewer galaxies appear along that line of sight, consistent with a supervoid. But other surveys find the dip is marginal, barely statistically significant. Critics argue the evidence is weak, that the supervoid might not be as large or as empty as claimed. Proponents counter that the surveys are not deep enough, that better data will confirm the void's existence. The Eridanus supervoid is controversial precisely because it is so enormous. Under standard cosmology, voids of this size are rare but not impossible. They form through gravitational instability, with matter flowing out of underdense regions into surrounding overdense regions. But there are limits. If a void is too large, it suggests matter is clumping more strongly than the standard model predicts. This could indicate faster structure growth, which might require changes to our cosmological parameters or even new physics. One proposed solution involves modified gravity. If gravity behaves differently on large scales, structures can grow faster. Voids can become deeper and larger. This would naturally produce supervoids like the Eridanus. But modified gravity theories have other implications. They affect galaxy rotation curves, gravitational lensing, and the cosmic microwave background. So far, observations have not strongly supported modified gravity over the standard model with dark matter. Another possibility is that the Eridanus supervoid is not a single structure, but several overlapping voids along the same line of sight. From our perspective, they would appear as one large underdensity. This would make it less unusual. Multiple smaller voids are easier to explain than one enormous void. But distinguishing between these scenarios requires precise distance measurements for thousands of galaxies, data that is difficult and time-consuming to collect. Regardless of its exact size, the region toward the cold spot does appear to have lower than average galaxy density. Something is there, or rather, something is not there. Whether it is a true supervoid or just a moderately large void cluster remains uncertain. Future surveys with better telescopes will provide answers. The Eridanus supervoid, real or not, highlights a deeper truth. The universe is far lumpier than we expected. Matter is not distributed smoothly. Huge structures exist that challenge our models, and every challenge is an opportunity to learn. The Milky Way sits on the edge of the local void, a region of low galaxy density about 200 million light-years across. This void is part of our immediate cosmic neighborhood, nestled within the Virgo supercluster, the larger structure of galaxies to which we belong. Our position is not random. We are being pulled. The local void has been known for decades. It is one of the closest large voids, making it relatively easy to study. Galaxy surveys show it clearly as a region with far fewer galaxies than average. The void sits in the direction opposite the Virgo cluster, the gravitational center of our supercluster. We are caught between the void behind us and the massive Virgo cluster ahead of us. This creates a gravitational gradient. The Virgo cluster pulls us toward it. The local void, having less matter, exerts less gravitational pull. The result is a net force dragging the Milky Way and our local group of galaxies toward Virgo at roughly 400 kilometers per second. This is our peculiar velocity, motion over and above the cosmic expansion. We are falling toward Virgo, and the local void is part of the reason. Standing at the boundary of the void means we have an unusual view of the universe. In one direction, toward the void, galaxies are sparse. In the opposite direction, toward Virgo and beyond, galaxies are abundant. This asymmetry affects our observations. Local measurements of cosmic expansion can be skewed if we do not account for our motion and position. We are not in an average location, and our measurements reflect that. The local void is not completely empty. It contains a few dwarf galaxies, small systems with relatively few stars. These dwarfs are notable because they appear to be moving toward the edges of the void, pushed or pulled by the denser regions surrounding them. This motion provides clues about how voids evolve over time. Matter continues to flow out of voids into filaments and clusters, making voids emptier and clusters denser as the universe ages. One interesting galaxy inside the local void is SO 461-36, a dwarf galaxy moving at 216 kilometers per second toward the void boundary. It is slowly escaping, like a pebble rolling downhill. Eventually, it will join the denser regions outside, adding its mass to the cosmic web. The void will be left even more empty. Our location near the local void has practical consequences. When astronomers measure distances to galaxies using methods like Cepheid variables or supernovae, they must correct for peculiar velocities. A galaxy that appears to be receding due to cosmic expansion might actually be moving toward or away from us due to local gravitational effects. The local void contributes to this motion. Ignoring it leads to errors in distance estimates, which propagate into errors in measuring the Hubble constant and other cosmological parameters. The local void is smaller than the KBC supervoid, which may encompass it. This raises questions about whether we are in one large structure or multiple overlapping voids. The boundaries are not sharply defined. Density decreases gradually as you move into a void, making it difficult to say precisely where one structure ends and another begins. The universe is expanding, but we cannot agree on how fast. Two different methods for measuring the expansion rate give two different answers, and the discrepancy is growing more significant as measurements improve. This is the Hubble tension, one of the biggest unsolved problems in cosmology, and it might be caused by the edges of cosmic voids. The Hubble constant describes how fast the universe expands. It tells us how quickly galaxies recede from us as a function of their distance. Measure the constant accurately, and you unlock fundamental properties of the cosmos: its age, its fate, the balance of matter and energy. But getting an accurate measurement is fiendishly difficult. One method looks at the cosmic microwave background, the light from the early universe. By analyzing temperature fluctuations in this ancient light, astronomers can infer the expansion rate 13.8 billion years ago. They then use models to calculate what the expansion rate should be today. This method gives a Hubble constant of about 67 kilometers per second per megaparsec. The second method uses supernovae in distant galaxies. Type Ia supernovae explode with a predictable brightness, making them excellent distance markers. By measuring how bright they appear and how fast they are receding, astronomers calculate the expansion rate directly. This method gives a Hubble constant of about 73 kilometers per second per megaparsec. 6 kilometers per second per megaparsec might sound like a small difference, but it is not. The measurements are precise enough that the discrepancy is statistically significant at the 5 sigma level, meaning there is less than a 1 in a million chance it is random fluctuation. Something is wrong. Either our measurements have systematic errors we have not identified, or our model of cosmology is incomplete. Enter the supervoids. If Earth sits in a large underdensity, like the KBC supervoid, local measurements could be biased. Galaxies, moving away from us inside the void, are also being pulled outward by the denser matter beyond the void's edge. This creates additional peculiar velocity on top of cosmic expansion. From our perspective, galaxies appear to recede faster than they would in a uniform universe. We measure a higher Hubble constant because we are in a special location. This explanation is controversial. Critics point out that astronomers already try to account for peculiar velocities by excluding very nearby galaxies from their measurements. Supernovae, closer than about 300 million light-years, are not used precisely to avoid local motion, contaminating the results. Only galaxies between 300 million and 2 billion light-years are included. But if the KBC supervoid is 2 billion light-years across, it affects that entire range. Proponents of the void hypothesis argue that the effect extends even beyond the void's physical boundary. Galaxies outside the void are also pulled toward the denser regions farther out, creating a gradient of peculiar velocities. Correcting for this requires knowing the void's exact size, shape, and depth, all of which are uncertain. Alternative explanations for the Hubble tension exist. Perhaps dark energy has changed over time. Perhaps there are additional particle species we have not detected. Perhaps our model of the early universe is slightly wrong. Each possibility has implications. If the supervoid explanation is correct, it means we are not measuring the global Hubble constant, but rather a local value skewed by our environment. The true constant would be closer to the CMB value, and the tension would dissolve. But if the supervoid does not explain the tension, something more fundamental is wrong. We might need new physics. Imagine waiting forever, standing at the edge of time itself, looking out into the cosmos. What is the farthest distance from which light could ever reach you, even if you waited an infinite amount of time? That distance is called the future visibility limit, and it sits at 63 billion light-years. This boundary is fixed in co-moving coordinates, meaning it does not change as the universe expands. It represents the ultimate edge of what is theoretically observable, given enough time. Today, our observable universe extends to 46 billion light-years. But if we wait long enough, we will eventually see light from regions now 63 billion light-years away. That is the absolute maximum. Why does such a limit exist? Because the universe is dominated by dark energy, which accelerates expansion. Far in the future, space will expand so rapidly that even light emitted today from distant regions cannot overcome the expansion to reach us. There is a cut-off distance beyond which light emitted now will never arrive, no matter how long we wait. That cut-off is the future visibility limit. Here is the strange part. As time passes, the observable universe grows, approaching the future visibility limit, but the cosmic event horizon shrinks. These two boundaries move in opposite directions. Eventually, the observable universe will stabilize at 63 billion light-years, while the event horizon settles at about 17.6 billion light-years. We will be able to see far more of the universe than we can ever influence or communicate with. This creates a frozen portrait. Billions of years from now, astronomers will observe a cosmos filled with galaxies out to 63 billion light-years. But nearly all those galaxies will be beyond the event horizon. The light arriving from them will have been emitted long ago when they were closer. Observers will watch ancient history play out, seeing galaxies as they were in the distant past, but unable to send signals back. The galaxies themselves will appear strange. Those near the future visibility limit will be extremely redshifted, their light stretched into infrared and radio wavelengths. They will appear to move in slow motion as time dilation effects become extreme. Stars in those galaxies will take subjective years to complete orbits that normally take millions of years. Supernovae will bloom and fade over eons. As dark energy continues to dominate, the future visibility limit remains at 63 billion light-years in co-moving distance. But in proper distance, it recedes faster than the observable universe expands. In other words, galaxies at the future visibility limit are moving away from us faster than new galaxies enter our view. The number of observable galaxies stops growing and begins to decline. This leads to a dark fate. In the far future, trillions of years hence, the observable universe will contain only the local group of galaxies. Everything else will have crossed the cosmic event horizon and faded from view. The future visibility limit will still be at 63 billion light-years, but it will be an empty shell. Light from those distant regions will have long since arrived and ceased. Nothing new will come. The future visibility limit marks the absolute boundary of cosmic information. Beyond it, no signal can ever reach us, even in principle. It is the ultimate edge of the knowable universe. Light does not always arrive as it was sent. Every photon from a distant galaxy is stretched by cosmic expansion, increasing its wavelength. Visible light shifts toward red. Red light shifts into infrared. Infrared shifts to microwave. This is cosmological redshift, and it gets more extreme with distance. Far enough away, photons are stretched so severely they become undetectable. Galaxies disappear into the redshift graveyard. Redshift is measured by comparing spectral lines. Hydrogen emits light at specific wavelengths, creating bright lines in a spectrum. If those lines appear shifted toward longer wavelengths, the source is receding. The amount of shift tells us how fast. For nearby galaxies, redshift is small, a few percent. For distant galaxies, redshift can be 1, 2, even 10 times the original wavelength. The most distant galaxies we have detected have redshifts above 10, meaning their light has been stretched to 11 times its original wavelength. As redshift increases, galaxies grow dimmer. Not only is each photon stretched, but photons arrive less frequently. A galaxy emitting 1 photon per second in its own frame might deliver only 1 photon every 10 seconds to us due to time dilation, another effect of expansion. The combination of wavelength stretching and time dilation reduces the energy we receive by a factor related to the square of 1 plus redshift. High redshift galaxies are extraordinarily faint. This creates a practical horizon. Even if a galaxy is within our particle horizon, we might not detect it if the redshift is too extreme. Photons stretched into radio wavelengths carry so little energy that they are indistinguishable from background noise. Telescopes have sensitivity limits. Below a certain signal strength, galaxies vanish into the noise floor. This is the redshift graveyard, where objects exist but cannot be observed. The James Webb Space Telescope pushes this boundary further than ever. Built to detect infrared light, it can see galaxies with redshifts above 10, catching light from when the universe was less than 500 million years old. These galaxies appear red and dim, their original ultraviolet and visible light stretched into infrared. But even Webb has limits. Galaxies beyond a certain redshift remain invisible, their light too faint or too shifted to detect. As galaxies cross the cosmic event horizon, they do not disappear instantly. Instead, they fade. Redshift increases without bound as they approach the horizon. The last photons we receive from them are infinitely redshifted, stretched to infinite wavelength, carrying zero energy. In practice, they become undetectable long before reaching this mathematical limit. The galaxy dims, reddens, and vanishes into the graveyard. Billions of years from now, the redshift graveyard will claim nearly everything. Galaxies beyond our local group will have crossed the event horizon. Their light will have been stretched beyond detection. Future astronomers will look up and see a universe that appears almost empty, not because it is empty, but because light from distant galaxies has redshifted into invisibility. The redshift graveyard is not a place, it is a state. Galaxies enter it when their light becomes too stretched to observe. They remain there forever, invisible, beyond the reach of any telescope. And as the universe expands, the graveyard grows. The universe is not smooth. Galaxies do not float randomly through space. They cluster, forming vast structures that stretch across hundreds of millions of light years. This is the cosmic web, a network of filaments, walls, nodes, and voids that defines the large-scale structure of the universe. And at its edges, matter thins until voids dominate. The cosmic web forms through gravitational instability. After the Big Bang, quantum fluctuations created tiny differences in density. Some regions had slightly more matter, others slightly less. Gravity amplified these differences. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over billions of years, this process created the cosmic web. Filaments are the highways of the cosmic web. Long, narrow structures where galaxies concentrate, spanning tens to hundreds of millions of light years. They contain a significant fraction of all galaxies. Filaments connect nodes, the intersections where multiple filaments meet. Nodes host massive galaxy clusters, the largest gravitationally bound structures in the universe. Clusters contain hundreds or thousands of galaxies packed into a few million light years. Walls are two-dimensional sheets of galaxies, thinner than filaments, but wider. They form the boundaries between voids, like the surfaces of soap bubbles. Galaxies in walls are more spread out than in filaments, but still denser than average. Walls can extend for hundreds of millions of light years, creating vast cosmic membranes. Voids are the empty spaces between filaments and walls. They occupy most of the volume of the universe, but contain few galaxies. Voids are not perfectly empty. They hold about 15% of the average cosmic density, including dark matter and gas. But that is enough for them to appear nearly empty compared to the dense filaments surrounding them. The cosmic web has fractal-like properties. Zoom in on a filament, and you find it is made of smaller filaments. Zoom in further, and those are made of galaxy clusters. Zoom out from the observable universe, and if there were a view from outside, you might see larger structures still. This self-similarity extends across many scales, though it eventually breaks down at the largest scales where the universe becomes statistically uniform. Voids evolve over time. Small voids merge into larger ones as galaxies flow out into filaments. The cosmic web becomes more pronounced with age. In the early universe, The web was barely visible, just subtle density fluctuations. Today, it dominates the large-scale structure. In the far future, it will become even more extreme, with nearly all matter concentrated in a few massive clusters separated by enormous voids. The boundaries of the cosmic web are not sharp. Density transitions gradually from filaments to voids. There is no line where the filament ends and the void begins. Instead, there is a gradient. This makes defining structures difficult. When does a small underdensity become a void? When does a cluster of galaxies become a filament? Definitions are somewhat arbitrary. The cosmic web is the skeleton of the universe. Galaxies are the flesh, filling in the structure, and voids are the spaces between, the edges where matter runs out and emptiness takes over. Cross the boundary of a cosmic void, and density drops sharply. Not instantly, but over a relatively short distance. The number of galaxies decreases by a factor of 5, 10, or more. This is the matter density cliff, the transition zone at the edge of voids where the universe changes character. Voids are defined by having significantly lower density than average. The threshold is typically set at less than 1/10 the cosmic mean density, though some voids are even emptier. Cross into a void, and you leave behind the busy cosmic web. Galaxies become sparse. Dark matter halos thin out. Gas clouds dissipate. What remains is a quiet, empty expanse. The density cliff is not a wall. It is a gradient spanning tens of millions of light years. Density decreases smoothly as you move from a filament into a void, but the transition happens faster than you might expect. Simulations show that void edges are relatively sharp compared to the void's overall size. A void 100 million light-years across might have an edge zone only 10 million light-years wide. This sharpness has consequences. Galaxies near the edge of a void experience a strong gravitational gradient. On one side, the dense filament pulls. On the other, the nearly empty void exerts minimal pull. The net force drags galaxies toward the filament and away from the void. Over time, this depopulates voids and makes them even emptier. The density cliff steepens. Galaxies caught in the cliff zone are interesting objects. They are typically small, dim, and metal poor. They have trouble forming stars because gas is scarce. Supernova explosions can blow gas out of the galaxy entirely, and there is no surrounding gas reservoir to replenish it. These galaxies are evolutionary backwaters, slow to grow and develop. The density cliff also affects cosmic expansion. Inside a void, expansion proceeds slightly faster than in dense regions. This seems counterintuitive, but it follows from general relativity. Dense regions have stronger gravity, which slows expansion locally. Voids have weak gravity, so expansion faces less resistance. Over billions of years, this causes voids to expand faster than the cosmic average, growing larger while filaments stay relatively compact. This differential expansion contributes to the Hubble tension. If we sit near the edge of a large void, local expansion could be faster than the global average. Supernovae measurements would return a higher Hubble constant because we are measuring expansion in an underdense region. The density cliff separates the local and global expansion rates. Mapping density cliffs is difficult. It requires precise distance measurements for many galaxies to determine where density drops. Galaxy surveys provide this data, but incompleteness is a problem. Faint galaxies are missed, especially in voids where galaxies are already scarce. This makes void boundaries fuzzy and uncertain. The matter density cliff marks the edge of the structured universe. Beyond it, the cosmic web fades. Matter becomes sparse. The universe looks different, emptier, quieter. It is not a dramatic boundary, like the event horizon, but it is real. Cross the cliff, and you enter a different regime, one where gravity is weak and expansion dominates. 14 billion light-years away, space expands so fast that galaxies at that distance recede from us at exactly the speed of light. This is the Hubble sphere, a boundary where recession velocity equals light speed. Beyond it lies the superluminal barrier, where galaxies recede faster than light. And yes, we can see many of them. The Hubble sphere is not a physical edge. It is a geometric consequence of cosmic expansion. Space expands everywhere at a rate described by the Hubble constant. The farther away something is, the more space lies between us, and therefore the faster it recedes. Recession velocity is proportional to distance. At the Hubble sphere, that velocity reaches light speed. Beyond it, recession exceeds light speed. This does not violate relativity. Special relativity only restricts motion through space. It says nothing about how fast space itself can expand. Galaxies beyond the Hubble sphere are not moving through space faster than light. Space between us and them is expanding faster than light. The distinction matters. Photons leaving a galaxy beyond the Hubble sphere initially move away from us, carried backward by expansion. The galaxy is receding so fast that even light aimed in our direction loses ground. But the photons do not give up. They continue traveling through space at light speed, and as they travel, they enter regions where space expands more slowly. Eventually, they reach zones where expansion is slower than light speed. Once they cross the Hubble sphere inward, they begin making progress toward us. This creates a strange situation. A photon spends billions of years traveling through space, initially moving away from Earth because expansion dominates, then gradually slowing its retreat as it enters slower expanding regions, finally reversing direction and heading toward us. The total journey can take longer than the age of the universe, because the photon spent time going the wrong direction. Most galaxies we observe have always been beyond the Hubble sphere. Their light was emitted when they were receding faster than light, yet we detect that light because it eventually crossed into subluminal regions. In fact, the most distant galaxies visible today are currently receding at more than 3 times the speed of light. Their recession velocity has only increased since they emitted the light we now see. The Hubble sphere shrinks over time. As dark energy accelerates expansion, the distance at which recession velocity equals light speed decreases. Today, it sits at about 14 billion light-years. In the far future, it will be closer. Eventually, the Hubble sphere will contract until it is slightly larger than the cosmic event horizon. At that point, almost no photons from beyond the Hubble sphere will ever reach us. The superluminal barrier is psychologically unsettling. Our brains evolved to understand motion through space, not motion of space. The idea that we can observe objects receding faster than light contradicts intuition. Yet it is reality. The universe operates on scales where intuition fails. Space expansion is not motion, it is geometry. Understanding the superluminal barrier is key to understanding cosmic horizons. The event horizon sits beyond the Hubble sphere. Galaxies beyond the event horizon are receding faster than light and always will be. The space between us and them expands so rapidly that photons emitted now can never reach us. The superluminal barrier is not the edge of visibility, but it is the edge of what is easily understood. There exists a sphere around Earth, roughly 16 billion light-years in radius, that defines everything we can ever influence. Send a signal today in any direction, and it will only reach destinations inside this sphere. Beyond lies the causal boundary, a dividing line between what we can affect and what remains forever beyond our reach. This boundary is the cosmic event horizon, but viewed from the perspective of causality rather than observation. Causality means cause and effect. If you cannot send a signal to something, you cannot cause anything to happen there. No information, no force, no interaction. The causal boundary severs the universe into regions that can interact and regions that cannot. Consider a galaxy sitting just beyond the causal boundary today. If you broadcast a radio signal toward it, that signal will never arrive. The expansion of space carries the galaxy away faster than your signal can travel. The signal chases the galaxy, but loses ground every moment. Eventually, the signal itself crosses the event horizon and is lost, redshifted into oblivion, never reaching its target. This creates a profound isolation. Civilizations beyond our causal boundary might as well exist in separate universes. They cannot affect us. We cannot affect them. No trade, no communication, no war, no cooperation. The expanding space between us guarantees eternal separation. We are causally disconnected. The causal boundary is shrinking. Today, it sits at 16 billion light-years. But as dark energy accelerates expansion, fewer galaxies remain within reach. Every moment, galaxies slip across the boundary and are lost. The sphere of influence contracts. In the far future, it will stabilize at about 17.6 billion light-years in co-moving coordinates, but fewer galaxies will occupy that space because many will have already crossed the threshold. Imagine a future civilization attempting interstellar colonization. They build generation ships, traveling at a significant fraction of light speed toward distant galaxies. But if they choose targets beyond the causal boundary, the mission is doomed from the start. The galaxy will recede faster than the ship can travel. The ship will never arrive. It will chase an ever-retreating target until it runs out of fuel and drifts in intergalactic space. This is not hypothetical. It is measurable reality. We can calculate exactly which galaxies are within reach and which are not. Andromeda is well inside the causal boundary. We will collide with it in a few billion years, but distant galaxies visible in our telescopes are already beyond reach. We see their past, but we cannot interact with their present or future. The causal boundary also affects the ultimate fate of intelligence. If a civilization hopes to expand indefinitely, colonizing the universe, the causal boundary sets a hard limit. You can only ever colonize regions inside your cosmic event horizon. Once dark energy dominates, that region stops growing and begins to shrink. The universe becomes a collection of isolated pockets, each containing a few galaxy clusters, separated by uncrossable voids. Some physicists speculate about ways to circumvent the causal boundary. Wormholes, if they exist and can be stabilized, might connect distant regions of space without traveling through the expanding space between. Warp drives, which compress space ahead and expand it behind, might outrun expansion, but these ideas remain speculative. No known physics allows circumventing the causal boundary. The causal boundary is final. It is not a temporary obstacle, but a permanent feature of an accelerating universe. Cross it, and you are severed from the rest of existence. On the other side, galaxies continue thriving, evolving, creating. But we will never know. They are beyond the edge of causation itself. 380,000 years after the Big Bang, the universe cooled enough for light to travel freely. Before that moment, space was opaque, filled with plasma that scattered photons endlessly. After that moment, light streamed through the cosmos unimpeded. The transition created a wall, the CMB wall, the oldest light we can detect. Beyond it lies a universe we cannot see. The cosmic microwave background radiation forms a glowing shell around us. It comes from every direction, arriving from a distance of 46 billion light-years. This is the surface of last scattering, the moment when photons decoupled from matter and began their journey toward us. The CMB wall is the edge of the visible universe in time, the farthest back we can see using light. The plasma before decoupling was opaque like fog. Photons bounced off electrons constantly, unable to travel far before colliding again. This scattering created a thermal equilibrium, with photons and matter at the same temperature, around 3,000 degrees. The universe glowed like the surface of a star, but the glow was trapped, unable to escape the plasma. As the universe expanded, it cooled. When the temperature dropped below 3,000 degrees, electrons combined with protons to form neutral hydrogen atoms. This process is called recombination, though it was actually the first time atoms formed. With electrons locked in atoms, photons no longer had free charges to scatter off. Suddenly, the universe became transparent. Light traveled freely, and the CMB wall was born. That light has been traveling ever since, 13.8 billion years of travel. During that time, the universe expanded by a factor of about 1,000. The light, originally visible and orange-red, stretched into microwaves. Today, the CMB has a temperature of 2.7 degrees above absolute zero. It is the coldest light in existence, and the oldest. The CMB wall is remarkably uniform. Temperature variations are only 1 part in 100,000. This uniformity is puzzling. Regions of the CMB, separated by more than a few degrees on the sky, were never in causal contact before decoupling. They could not have exchanged information, yet they have almost exactly the same temperature. How did they coordinate? This is the horizon problem, one of the motivations for cosmic inflation theory. Inflation solves the problem by proposing that the universe expanded exponentially in the first fraction of a second, stretching a tiny, causally connected region to cosmic scales. Regions that appear disconnected in the CMB were actually in contact before inflation. They had time to reach the same temperature. Then inflation stretched them apart faster than light. The uniformity of the CMB wall is evidence for inflation. But the CMB wall is not perfectly smooth. Tiny fluctuations exist, seeds of galaxies. Denser regions appear slightly warmer because photons climbing out of their gravitational wells lose energy. Less dense regions appear cooler. These fluctuations map the distribution of matter when the universe was 380,000 years old. They are the blueprint for all structure that formed later. The CMB wall is an impassable barrier for light. We cannot see past it using photons, but other signals can penetrate. Neutrinos decoupled from matter even earlier, creating a cosmic neutrino background. These neutrinos have not yet been detected, but they carry information from when the universe was 1 second old. Gravitational waves decouple immediately, potentially carrying information from the Big Bang itself. Future observatories might detect these signals and peer beyond the CMB wall. For now, the CMB wall marks the edge of the visible universe. Beyond it lies an opaque universe, forever hidden from optical observation. It is the ultimate wall, older than any structure, a boundary written in the oldest light. Time can be measured in different ways. Proper time is what clocks measure, the ordinary passage of seconds, years, eons. But cosmologists use another kind of time called conformal time, which accounts for cosmic expansion. In conformal time, the Big Bang happened an infinite conformal time ago, and the far future will occur at an infinite conformal time from now. This creates boundaries at infinity. Conformal time is a mathematical tool. It compresses the infinite proper time of an eternally expanding universe into a finite conformal time interval. This makes calculations easier. Light rays travel at 45-degree angles on conformal time diagrams, simplifying visualization. But conformal time also reveals fundamental limits. The particle horizon in conformal time is finite. Light can only travel a limited conformal distance since the Big Bang. This distance defines what we can observe. As proper time approaches infinity, conformal time approaches a finite limit. That limit is the conformal time horizon, the maximum conformal distance light can ever travel. Beyond it, space is forever unreachable. Imagine proper time stretching infinitely into the future. Stars burn out, galaxies fade, black holes evaporate, protons decay. If they do, eventually, the universe contains only isolated particles separated by vast expanding space. Proper time continues forever, but conformal time approaches a finite value. In conformal coordinates, the far future is a boundary at a specific conformal time. This has strange implications. Events that occur infinitely far in the future, by proper time, occur at a finite conformal time. The particle horizon at conformal time infinity is the future visibility limit. Light from regions beyond that limit, emitted at any proper time, will never reach us because it would require infinite conformal time to arrive. The conformal time limit sets the absolute edge of observation. The math is abstract, but the consequences are concrete. There exists a maximum distance from which light can reach us, even if we wait forever. That maximum is 63 billion light-years in co-moving distance. It is the future visibility limit, expressed in physical units. But in conformal time, it is the horizon at time infinity, a boundary at the edge of the space-time diagram. Conformal time also affects the event horizon. The cosmic event horizon is our past light cone at conformal time infinity. It represents the boundary from which light emitted now could reach a distant observer in the infinite future. For us, it is the boundary beyond which we can send no signals. In conformal coordinates, this boundary is finite and fixed, even though proper time to reach it is infinite. These mathematical edges are not arbitrary. They reflect real physical limits imposed by cosmic expansion and light speed. The universe has geometry, and that geometry has boundaries. Conformal time makes those boundaries visible. Physicists use conformal time to study the causal structure of space-time. Light cones, horizons, and boundaries are easier to analyze in conformal coordinates. The Big Bang becomes accessible, not an infinite past, but a boundary at a specific conformal time. The far future similarly becomes accessible as a boundary rather than an unreachable infinity. The conformal time limit is where mathematics meets cosmology. It shows that infinity, at least in certain coordinate systems, is a finite boundary, and boundaries define edges, even at the end of time. Dark energy is accelerating the expansion of the universe, and this creates a new kind of horizon, not the particle horizon, which grows with time, and not the event horizon, which marks what we can influence. The dark energy horizon is the distance at which dark energy dominates so completely that structures can no longer grow. Beyond it, galaxies cannot form, matter cannot clump, the universe is torn apart. Dark energy behaves like a repulsive force, pushing space apart. On small scales, it is insignificant. Gravity easily overcomes it, binding galaxies and clusters together. But on large scales, dark energy wins. It drives cosmic acceleration, making distant galaxies recede faster and faster. At a certain distance, dark energy's repulsion exceeds gravity's attraction. That distance is the dark energy horizon. Current measurements place the dark energy horizon at roughly the same distance as the cosmic event horizon, about 16 to 17 billion light-years. This is not coincidence. Dark energy accelerates expansion, and acceleration creates event horizons. The two are linked. As dark energy strengthens its grip, the horizon contracts. Fewer regions remain gravitationally bound. Structures larger than the dark energy horizon cannot form. Imagine a proto-galaxy cluster attempting to collapse. If the cluster's extent exceeds the dark energy horizon, different parts of the cluster recede from each other faster than gravity can pull them together. The collapse fails. The cluster is ripped apart by expansion. Only structures smaller than the horizon can remain bound. This sets a maximum size for gravitationally bound structures. The largest galaxy clusters we observe are a few tens of millions of light-years across, comfortably within the dark energy horizon. Superclusters, which span hundreds of millions of light-years, are not gravitationally bound. They are temporary associations, dissolving as expansion carries their component clusters apart. The dark energy horizon prevents superclusters from ever collapsing into single structures. As the universe ages, the dark energy horizon shrinks in co-moving coordinates. This means fewer new structures can form. Galaxy clusters that are marginally bound today will be unbound in the future. Dark energy will pull them apart. The universe enters a phase where structure formation ends. No new galaxies, no new clusters, no new filaments. Existing structures persist if they are tightly bound, but everything else dissolves. This creates a future where the universe is divided into isolated regions. Each region contains a gravitationally bound cluster or group of galaxies. These regions are separated by expanding voids that grow faster than the clusters can attract each other. The dark energy horizon separates each island from every other. Within an island, gravity dominates. Between islands, dark energy dominates. Our own local group of galaxies, including the Milky Way and Andromeda, is within a single island. We will remain gravitationally bound, eventually merging into a single giant elliptical galaxy. But nearly everything else will disappear beyond our dark energy horizon. Future observers will see a universe containing only their own island, surrounded by darkness. The dark energy horizon is not static. If dark energy strengthens over time, the horizon contracts. Structures that are bound today might be torn apart tomorrow. If dark energy weakens, the horizon expands, allowing larger structures to form. Measuring how the horizon evolves over cosmic time reveals the nature of dark energy. Is it a cosmological constant, unchanging, or is it dynamic, evolving? Current evidence suggests dark energy is constant. If so, the dark energy horizon will stabilize at a fixed co-moving distance. Structures larger than this will dissolve. Structures smaller will endure. The universe will fragment into isolated islands, each surrounded by its own dark energy horizon, forever separated from all others. The observable universe is a sphere 93 billion light-years across, centered on Earth. This is not the entire universe. It is simply the region from which light has had time to reach us. Every location in the universe has its own observable sphere, and those spheres overlap. The observable universe shell is the boundary of our sphere, the edge beyond which we cannot see. Stand on the shell, hypothetically, and you would see 13.8 billion years into the past in one direction, toward the Big Bang. In the other direction, you would see 13.8 billion years into the past toward us. But because the universe is homogeneous on large scales, the view would look the same in all directions. The cosmic microwave background, galaxies forming, clusters evolving. The shell is not a special place. It is simply the edge of our view. The shell moves outward constantly. Light from farther regions reaches us every moment, expanding the observable sphere. The shell's recession velocity is enormous, far exceeding light speed. But this is motion of space, not through space. The shell represents the locus of points from which light emitted at the Big Bang is just now arriving. Objects on the shell today are not there anymore. They have moved, carried by expansion. When they emitted the light we now detect, they were much closer to us, perhaps only a few 100 million light-years away. Over the billions of years that light traveled, they receded to 46 billion light-years distance. If we could see them as they are now, they would look much older, but we cannot. We only see their past. The observable universe shell is not a physical boundary. You could cross it without noticing. If you traveled there, you would find galaxies, clusters, cosmic web, just like everywhere else. But from Earth, the shell marks the limit of visibility. Beyond it, light has not had time to arrive. Those regions are invisible, not because they are empty or dark, but because information from them is still in transit. What lies beyond the shell? More universe, possibly infinite. The shell does not mark the edge of existence, only the edge of observation. If the universe is infinite, the observable universe is an infinitesimal fraction of the whole. If the universe is finite, the observable universe might be a large fraction or a small fraction, depending on the universe's total size. The shell is also the approximate location of the cosmic microwave background. CMB photons reaching us today were emitted from the shell when the universe was 380,000 years old. The matter that emitted those photons has since moved far beyond the shell, carried by expansion. But the photons remained at the shell, traveling toward us at light speed while the shell expanded outward. In the far future, the observable universe shell will continue expanding, but at a slowing rate. As dark energy dominates, the rate of new regions entering our view decreases. The shell's expansion approaches the future visibility limit at 63 billion light-years. At that point, the shell stops growing. No new regions will ever become visible. The observable universe shell is a personal horizon. Every observer has their own shell, centered on their location. An observer in a distant galaxy sees a different observable universe, one that overlaps ours but is not identical. Regions visible to them are invisible to us, and vice versa. Each observer occupies the center of their own cosmic sphere. The shell is the edge of information. Beyond it, we have zero knowledge. It is a blank, unknowable expanse that might be identical to our observable universe or might be completely different. We cannot test which. The shell defines the limit of empirical science. 16 billion light-years away sits a shrinking sphere called the affectable universe. Everything inside this sphere can theoretically be reached by signals we send today. Everything outside is beyond influence. This sphere is smaller than the observable universe and getting smaller. Our reach is contracting. The affectable universe is defined by the cosmic event horizon. It represents all regions that can be causally affected by us if we act now. Send a light signal today, and it will reach destinations inside the affectable universe, given enough time. Send it toward anything outside, and it will never arrive. The signal will chase the target but lose ground as expansion accelerates. This creates an asymmetry between what we can see and what we can affect. We observe galaxies out to 46 billion light-years, but we can only affect regions within 16 billion light-years. The majority of the observable universe is already beyond our causal reach. We see it, but we cannot touch it. It is like watching a movie. The events are visible, but we cannot change them. The affectable universe shrinks continuously. Every second, matter crosses the event horizon and leaves the affectable sphere. Galaxies that were reachable yesterday are unreachable today. The sphere contracts at a rate determined by cosmic acceleration. In a few billion years, only the local group of galaxies will remain inside. Everything else will be lost. This has implications for any advanced civilization hoping to expand across the cosmos. There is a finite window of opportunity. Act now, and you can send probes to thousands of galaxies within the affectable universe. Wait too long, and those galaxies slip beyond reach. The universe imposes a time limit on expansion. Miss the window, and you are confined to your local cluster forever. Some futurists propose strategies to maximize the use of the affectable universe. Launch self-replicating probes at high speed toward distant galaxies. Each probe, upon arrival, builds more probes and sends them farther. This exponential colonization could theoretically reach a large fraction of the affectable universe before it shrinks too much. But even this strategy has limits. Probes travel slower than light. By the time they reach distant galaxies, those galaxies may have crossed the event horizon. The affectable universe also has philosophical implications. It limits the scope of possible influence. Any action we take, any signal we send, can only affect a finite region. Beyond that region, we might as well not exist. Our causal footprint is bounded. This is true for all observers, everywhere. Every civilization, every intelligence, is confined to a finite sphere of influence. As dark energy dominates, the affectable universe approaches a minimum size of about 17.6 billion light-years in co-moving coordinates. But the number of galaxies within that sphere decreases as galaxies cross the horizon. In the far future, the affectable universe will contain only our local galactic cluster. Future inhabitants will have no ability to affect anything beyond their immediate neighborhood. The affectable universe is the true edge of agency. Beyond it, free will and choice are meaningless. You cannot make decisions about things you cannot affect. The event horizon is not just a boundary in space. It is a boundary of possibility itself. Some galaxies are moving toward us but getting farther away. This sounds impossible, but it is happening right now to countless galaxies in the universe. They travel through space in our direction at hundreds of kilometers per second, yet the distance between us increases. The expansion of space overpowers their motion. This is the receding galaxy phenomenon. Picture a galaxy 3 billion light-years away, moving toward us at 500 kilometers per second. That is fast, roughly twice the speed of Earth, orbiting around the center of the Milky Way. But space between us and that galaxy is expanding at a much higher rate. At 3 billion light-years, expansion adds about 70 kilometers per second per megaparsec. That works out to roughly 21,000 kilometers per second of recession velocity due to expansion alone. The galaxy's motion toward us subtracts from the expansion. Instead of receding at 21,000 kilometers per second, it recedes at 20,500 kilometers per second. It is moving toward us but receding from us simultaneously. The galaxy is like a person walking forward on a treadmill that is rolling backward faster than they walk. They move forward relative to the treadmill but backward relative to the ground. This phenomenon occurs for galaxies beyond the Hubble sphere. Inside the Hubble sphere, expansion is slower than light, so a galaxy moving toward us at any speed will eventually arrive. Outside the Hubble sphere, expansion exceeds light speed. A galaxy moving toward us at light speed would still recede. Only if it could move faster than light would it make progress toward us. Since nothing moves through space faster than light, all galaxies beyond the Hubble sphere recede from us, regardless of their velocity through space. We can see many of these galaxies. Their light reaches us because it was emitted when the galaxy was closer inside the Hubble sphere. The light traveled toward us, crossing into subluminal regions, and eventually arrived. But the galaxy itself never reached us. It remains beyond the Hubble sphere, receding. The receding galaxy phenomenon creates counterintuitive situations. A galaxy could be moving directly toward us at a substantial fraction of light speed, yet we measure its redshift, indicating recession. The redshift comes from expansion, not from the galaxy's motion. The galaxy's velocity through space contributes a small blue shift, but the expansion redshift dominates. The net result is redshift. The galaxy appears to recede. Future observations will show this galaxy continuing to recede and accelerating. Its redshift will increase over time. Eventually, the galaxy will cross the cosmic event horizon. At that point, its motion toward us becomes irrelevant. Even moving at light speed directly toward us, it could never reach us. The expansion is too strong. The galaxy is lost. This phenomenon highlights the difference between cosmological recession and physical motion. Recession is not motion through space. It is motion of space. Galaxies are not flying away from us like shrapnel from an explosion. They are carried by the expanding fabric of spacetime. Their own motion through that fabric is secondary, often negligible compared to the expansion. The receding galaxy phenomenon affects how we interpret observations. Measuring a galaxy's redshift tells us its recession velocity, but not its velocity through space. To find the latter, we need additional measurements, like observing how the galaxy's position on the sky changes over time. This is difficult for distant galaxies because the motion is tiny, far below current observational limits. In the far future, nearly all galaxies beyond our local group will exhibit the receding galaxy phenomenon. They will all be moving away, carried by expansion, regardless of their individual velocities. The universe will empty itself, not because galaxies are fleeing, but because space itself is pulling them apart. Cosmic voids do not stay the same size. They grow. As the universe ages, voids expand, merging with neighboring voids to create even larger empty regions. This is the void evolution pattern, a process driven by gravity and expansion that reshapes the cosmic web over billions of years. Voids form because matter flows out of underdense regions into overdense regions. Early in the universe, density fluctuations were tiny. Some regions had slightly less matter, others slightly more. Gravity amplified these differences. Matter in underdense regions felt a net gravitational pull toward nearby overdense regions. It flowed outward, leaving the underdense region emptier. Over time, this created voids. Small voids formed first. Regions a few tens of millions of light-years across became underdense enough to be recognizable as voids. As matter continued flowing out, these voids expanded. Their boundaries pushed outward into the surrounding cosmic web. Galaxies near the edges were pulled away, either into filaments or into neighboring voids. The voids grew. When two voids expanded until they touched, they merged. The boundary between them dissolved. Matter that had separated them was pulled into filaments elsewhere. The result was a single, larger void. This process repeated throughout the universe. Small voids merged into medium voids. Medium voids merged into large voids. Large voids merged into supervoids. The cosmic web today is dominated by large voids. Most of the universe's volume is void. Galaxies occupy filaments and clusters, which collectively take up less than half the total space. This was not true in the early universe. When the universe was young, voids were small and filaments were more evenly distributed. The cosmic web has become more extreme over time, with voids growing and filaments densifying. The void evolution pattern continues. Future voids will be even larger. As the universe expands, existing voids inflate. Matter continues, flowing out of them into filaments. Mergers continue. The trend is toward fewer, larger voids separated by dense, compact filaments. Eventually, the cosmic web will consist of isolated galaxy clusters surrounded by enormous voids. Dark energy accelerates this process. In a universe without dark energy, expansion would slow down, allowing gravity more time to pull matter back into voids, potentially preventing further growth. But dark energy speeds up expansion, making it easier for voids to grow and harder for matter to fall back in. Voids expand faster and become emptier. Simulations of void evolution show fascinating structure. Voids are not perfectly spherical. They are irregular, with protrusions and indentations caused by the surrounding filaments. As voids merge, they form complex shapes, like clusters of soap bubbles. Over time, these shapes simplify as the voids relax towards spherical configurations. But new mergers continually disrupt the relaxation, keeping the shapes irregular. The void evolution pattern affects galaxy formation. Galaxies inside voids evolve differently than galaxies in filaments. They have less access to gas, fewer mergers, and slower star formation rates. They remain small and dim. As voids grow, these galaxies become more isolated. Their evolution slows further. They are evolutionary fossils, preserving conditions from earlier cosmic epochs. The pattern also affects the cosmic microwave background. Large voids create temperature fluctuations through the integrated Sachs-Wolf effect. As the universe ages and voids grow, this effect becomes more pronounced. Future observations of the CMB might reveal the shadows of enormous supervoids that have not yet fully formed. The void evolution pattern is the universe simplifying itself. Complex, tangled structures in the early cosmic web are being sorted into simple categories: dense filaments and empty voids. The universe is separating matter from emptiness, concentrating galaxies into smaller regions and leaving vast tracts of space nearly devoid of material. Supervoids are too large. According to standard cosmology, matter should be distributed relatively uniformly on large scales. Density fluctuations should decrease with size. Small regions can be very dense or very empty, but large regions should average out to near the cosmic mean. Supervoids violate this expectation. They are enormous and significantly underdense. This is the supervoid paradox. The KBC supervoid stretches 2 billion light-years across, with 20% less matter than average. The Eridanus supervoid, if confirmed, is 500 million to 1 billion light-years across. The Botas void is 330 million light-years across, with 90% less matter than expected. These structures are rare in standard cosmological models. Simulations predict they should be exceedingly uncommon, yet we observe them. One possibility is that we are simply lucky. Rare events happen. Perhaps we live in an unusual part of the universe where supervoids happen to form. Statistical outliers exist, and somebody has to observe them. This explanation is unsatisfying, but not impossible. The universe is large. Unlikely structures are expected somewhere. Another possibility is that our cosmological models underestimate structure growth. Perhaps matter clumps more strongly than we think, creating deeper voids and denser filaments. This could happen if dark matter interacts in unexpected ways, or if dark energy has different properties than assumed, or if gravity behaves differently on large scales. Each of these would affect structure formation. Modified theories of gravity, like modified Newtonian dynamics, predict stronger structure growth. In these theories, gravity is more effective at pulling matter into overdense regions, leaving voids deeper and larger. Supervoids are easier to explain, but modified gravity theories must also match other observations, like galaxy rotation curves, gravitational lensing, and the cosmic microwave background. So far, no modified theory matches all observations better than standard cosmology with dark matter and dark energy. A third possibility is measurement error. Perhaps supervoids are not as large or as empty as they appear. Galaxy surveys are incomplete. Faint galaxies are missed. Dark matter is invisible and must be inferred. If dark matter fills supervoids more than expected, they might be less extreme than measurements suggest, or they might consist of multiple smaller voids aligned along our line of sight, appearing as one large void from our perspective. The supervoid paradox matters because it tests cosmology at its limits. The largest structures in the universe are sensitive to cosmological parameters. Measuring their abundance and properties constrains models. If supervoids are more common than expected, something is wrong with our models. Either we misunderstand dark energy, or dark matter behaves strangely, or gravity needs modification. Current evidence suggests supervoids are rare but not impossible under standard cosmology. They exist at the tail end of the probability distribution. Observers are likely to find themselves near unusual structures simply because most observers exist near structures, and the rarest structures are unusual by definition. This anthropic reasoning is controversial, but it cannot be dismissed. The supervoid paradox also raises questions about our location. Why do we find ourselves near or inside multiple large voids? Is this coincidence, or does it tell us something about galaxy formation or observer distribution? Galaxies might form preferentially near void edges, where matter is funneled into filaments. If so, observers would typically find themselves near voids. We might be in a typical location for observers, even if it is an atypical location for the universe as a whole. Resolving the paradox requires better data. Deeper galaxy surveys will map voids more accurately. Measurements of dark matter distribution using gravitational lensing will reveal whether voids are truly as empty as they appear. Simulations with higher resolution will predict the expected abundance of supervoids more precisely. The answers are coming. The supervoid paradox is a crack in the edifice of cosmology, not a fatal flaw, but a sign that something interesting is happening at the edges of our understanding. The universe has many edges: the particle horizon, the event horizon, the Hubble sphere, the CMB wall, supervoids, the future visibility limit. Each marks a boundary, a transition, a place where something changes. But there is one edge that encompasses all others, one final boundary that defines the ultimate fate of the cosmos, the edge where expansion never stops. Dark energy is driving the universe apart at an accelerating rate. If this continues forever, the cosmos is headed toward a cold, dark, lonely end. This is not collapse, it is the opposite. It is eternal expansion, asymptotically approaching a state called the de Sitter phase, where space inflates exponentially and all structure dissolves. In the far future, trillions of years from now, the universe will be nearly empty. Galaxies beyond our local group will have crossed the cosmic event horizon and disappeared from view. Stars will have burned out. Black holes will have evaporated through Hawking radiation. Even protons may decay, leaving only isolated particles drifting through expanding space. But expansion does not stop. Space continues growing, driven by dark energy. The distance between particles increases. The temperature approaches absolute zero. The universe becomes a vast, cold, dark expanse with almost no activity. This is heat death, the maximum entropy state, the ultimate edge of cosmic time. At this edge, the universe has no structure, no galaxies, no stars, no planets, no life. Only occasional random particles separated by distances that dwarf today's observable universe. The cosmic event horizon contracts to a fixed co-moving size, isolating each particle in its own causally disconnected bubble. Nothing can interact with anything else. The universe fragments into infinite loneliness. This fate is not certain. It depends on dark energy remaining constant. If dark energy weakens over time, expansion might slow. If it strengthens, expansion could accelerate catastrophically, tearing apart galaxies, stars, planets, and eventually atoms. This is the Big Rip, a scenario where the ultimate edge arrives much sooner, destroying all structure in a finite time. Current observations suggest dark energy is constant, consistent with a cosmological constant. If so, the universe expands forever, but at a steady, accelerating rate. The ultimate edge is infinitely far in the future by proper time, but it is a real destination. The universe is heading there. Some physicists speculate about escape routes. Perhaps intelligent civilizations could harness dark energy or manipulate the vacuum to reverse expansion locally. Perhaps they could create stable structures that resist being torn apart. Perhaps they could retreat into lower energy states, becoming simpler and slower to endure the cold future. These ideas are speculative, far beyond current technology or understanding. The ultimate cosmic edge is also a philosophical edge. It is the end of complexity, the end of change, the end of meaning. In a universe with no structure, no interactions, and no observers, what is left? The question forces us to confront the finite lifespan of the cosmos. The universe had a beginning at the Big Bang. It will have an end, not in collapse but in dissolution. Yet even at the ultimate edge, the universe does not disappear. Space continues existing. Vacuum energy continues driving expansion. Perhaps quantum fluctuations continue creating random events, infinitely rare but inevitable over infinite time. Perhaps the universe enters a state that allows new beginnings, new cycles, new structures. We do not know. What we know is that the universe has edges everywhere we look, boundaries in space, time, causality, and observation. These edges define what is possible and what is not. They set limits on knowledge, influence, and existence itself. The universe is finite in many ways, even if it is infinite in extent. The ultimate cosmic edge is not a place you can visit. It is a destiny, a direction, an end state written into the fabric of spacetime by the relentless acceleration of dark energy. It is the edge where all other edges converge, the boundary at the end of cosmic time, the final darkness after the last light fades, and it is approaching, not quickly, not within any human timescale, but inevitably. The universe is heading toward its ultimate edge, and nothing can stop it.